you. The real talk. Here it is. Okay, Microsoft Management Summit. Go down here. My name is James McCaffrey. I work at Microsoft. I work at Microsoft Research, which means I'm sort of, this talk is considered sort of an out-of-band talk, where there's nothing that you can go back to and immediately put to use, I don't think. This is somewhat forward-looking and something that you may be able to use. I'm going to focus on several things, but in fact, I had to write this out because I was afraid I was going to forget. But there's really three goals that when you leave here at 5:15, not 5:45, we'll go 45 minutes. And you know what, there's a clock up. I did the worst thing ever one time. I thought I was going to be so cool. On my own PowerPoint slide, you know, PowerPoint does not have a thing in here that you can put down a countdown clock. I always wondered, why is that not there? That would be so cool, so you know how much time is left. So I put one in. I hacked one together, you know, using COM and all that stuff. And of course, that was the worst thing ever because no one was paying attention to the talk. Everyone was just winding down, you know, just focusing on how much time is left, like when you were in school watching the clock instead of listening. Okay, so that was a bad idea. But there's three goals here. First of all, the most important thing is to know when neural networks might be applicable. There are so many things where identifying the right problem is the most important part. See, right now, if I asked you, and I'll have a slide, give me a specific concrete example of when you might want to think about neural networks, you might have trouble coming up with that. But when you leave this presentation, you'll be able to be very concrete on what kind of problems it solves and what kind of problems it doesn't solve. Number two, it turns out that these neural networks are sort of like the mother of all machine learning techniques. And it turns out that they're not easy. They're very complicated. And one of the hard parts is knowing why you can't just like press and play and say, here, solve this for me. I will identify what the issues are, you know, what the tricky parts are, very clearly and in one slide. Now for that, you won't remember that information when you leave here. See, the first part you will. The actual, what are the specific roughly 7 things that are the tricky parts, you can refer to this presentation after the fact and go through, because they're all in one place. And I haven't seen them anywhere. They're talked about all over the place on the internet. And the third thing is, know how to learn more. In other words, if you want to know more, where do you go? Because right now, it's not that there aren't resources on neural networks out there. There's too many. And I'm going to point you to the 3. I go, okay, go to here, here, or here. End of story. So that's the goals of this talk. Now, here's the agenda. And so I challenged you at the beginning. There's only one thing that matters up here at all, and it's really kind of a joke. Just think of me as the cynical old guy who's in the last few dying steps of his career, okay? Cranky, cynical old guy. And you, sir, said that you think that you know what the only important thing up there is. Shout it out. Okay, so his answer was slide 1 is the most important thing. What kind of problems does it solve? Because that, you can't get started unless you know. Okay, so technically he's correct, but cynically he's incorrect. We got to vote for slide 9. That was also a correct answer because that's, it boils it down. You can just go to that one slide. We got to vote here. Okay, he hit it, yes. Okay, you're only going to be tortured for 10 slides. Okay, when I was growing up, I worked at Disneyland in Southern California. Have you ever been to Disneyland or Disney World? Yeah, well, don't. Okay, but if you have, you're forced to go. You'll see people standing in line for 3 hours. 3 hours for a 10-minute ride. I kid you not. Now, some of those people are happy, and some of those people are not happy. And the reason is, what I learned is that people do not mind being tortured as long as they know the extent of the torture. Okay, you're going to be tortured at maximum 10 slides. This is like the airport. Have you ever gone to the airport and you just get flight delayed? Your flight, okay? And you just go, oh, crap. See, it doesn't matter if they tell you, we've got a mechanical problem, it's probably going to take 3 hours to fix this. You go, okay, I can deal with that, as opposed to flight delayed and you have no knowledge of how long you're going to be tortured for. So I'm kind of joking. You'll be tortured for 10 slides. What I'm going to do is, I don't know if what I like to do is I'm going to walk through the entire presentation real fast so you can get an overview of what it looks like. That'll help you determine if you want to sit and stay through the presentation or not. It'll also give you a rough idea of, like, if you start getting bored, you go, shit, thank goodness we're on slide 8 and we're almost done. So it looks something like this. Here's the whole presentation. I'm going to go through and the types of problems that it solves. This is sort of the internal kind of thing, the classic picture that you'll see everywhere. But there's a lot of information there that I'll summarize. This is also internal information. This is one of the issues. I said there's technical things that you have to know about. And I'm not going to explain how to solve all these things, but I'm just going to identify what they are so that you know, all in one presentation, what do I have to figure out? Here's sort of this conceptual thing. This is an important slide up there, the 6 main alternatives. It's not enough to know, you got to know what kind of problems something solves. It's equally important to know what your alternatives are, right? And we'll talk about that. Talk about training. This is one of those technical issues. Training error, that's part of the same thing, same slide really. Model overfitting, this is another one of those key things that you got to understand in a way that I'll explain later. It turns out that there are 2 ways you can do neural networks. You can use them with an existing tool, and that's the main one, or you can do it with custom code, and that's the main way to do that. I'll explain this. There's the summary and takeaways. There's the resources, including, as I mentioned earlier, the last one is my personal blog, and I will post this presentation on that blog so that you can get at it from anywhere. If for some reason it doesn't make it onto like if I start slamming Microsoft and I get fired, then they won't post my presentation or something like that. See, you're supposed to be laughing at that point. Apparently hey Justin, do we have one of those big signs that says laughter and applause or something that pop up? So to work on that, please. I think we're going to need it. And then the thank you, where you'll give me a huge round of applause. Now, before we launch in, and I'm really sort of shuffling here for reasons. As a Microsoft thing, they gave us a sort of a template to use. That's why my presentation looks a little bit too fancy for me, but I wanted to, toe the company line, use the right template. But they gave us a bunch of icons. And they just said, here's the icons you can use on your presentation. Now, later on, I found out what those mean because they were part of the program. But pretend like, if you've seen these before, pretend like you've never seen these before, and tell me what the heck those are supposed to mean. I had no idea. So star. Okay, I'll just put a bunch of stars in my presentation. Next one. What does that mean to you, the arrows? Sorry, what? Browser? See, for me, it meant like a little joystick kind of thing. Or, I'm lost. I don't know which way to go. Okay, the next one. Clearly, meth lab. I'm going, I don't see why there's anything chemistry going to involve in any of these talks. A computer. Yeah, that's going to be real useful. Police riot, like move away from the burning building or something. Okay, then a fat pen. Apparently, I read that as a Bible, but it's not. Next, some sort of a old-fashioned quill. I was thinking a Declaration of Independence kind of thing. And then last one, I don't know. So anyway, I'm sorry. If you were expecting to see some fancy icons in the presentation, you're going to leave disappointed because I did not know how to use my fancy icons. I'm sorry, what? Wait, could someone repeat? Which one of those icons is? None. I was thinking about making up my own dummied ones with, but then that was because I have no graphic ability whatsoever, so I gave up. Okay, so there's the agenda, and basically we just ran through it and I've explained it. So here is arguably the most important slide, or tied for. What kind of a problem does a neural network solve? Well, in my mind, this is what pops up. If you have something like this, then neural network is a possibility. But let's look at this pretty carefully. So, in fact, this is like an Excel spreadsheet. First point, data. A neural network works on data. And one of my themes here is that one of the things I've seen going on in the IT world is that we're gathering more and more data for a lot of reasons. Log files, all kinds of files, and especially with the move to the cloud, a lot of this data can be gathered for you automatically. However, every company, one of the biggest things going on in the Pacific Northwest where I work is Amazon.com just generates, the amounts of data they generate is beyond comprehension. Every time you go on Amazon.com, they gather how long you spend, how long you hover, your path through the site, every click, everything, just massive amounts of information, and it's not uncommon for 1 million users to be online simultaneously. So there's just billions of data items there. But how do you make sense out of this? So this is, there's all kinds of data scientists, big data, all these things. But here's just a little thing. But we have some data. What's significant about this data with regards to neural networks, what we're going to see in a minute, is that this is sort of a hypothetical problem where we have some people, and I just, this is not realistic at all, but I made it accessible, something that I think most of us can identify with. So we've got, each one represents a person, and we've got the person's age, their annual income in US dollars, their sex, either male, female, or you can imagine sort of a undeclared or something like that, I don't know. Religion, none, Catholic, Judaism, Presbyterian Catholic. And then notice that it doesn't show up to, then there's like 2 lines there. Then the politics. So what we have here is a problem where we've got some data. And our goal is prediction. Neural networks can do lots of things, but what we're going to talk about is classification and prediction. Classification is where you have a bunch of data and you've got a certain class, and then the prediction part is you're trying to predict it. So that last line is, suppose we have someone who is 38 years old with $51,000 income, who is male, and who is Presbyterian, predict their politics. So I always like to think that neural networks boil down to prediction. Now, there are many of techniques, and I'll show you the 6 main alternatives to neural networks. But in a nutshell, neural networks are considered the most powerful of all. By the way, this is called machine learning. And there's all kinds of vocabulary here. It used to be called artificial intelligence, but that has sort of a bad taint to it, to some extent. So now we call it machine learning. There are many techniques, but one of the reasons why neural networks is so powerful is that, notice the data that the predictor data, okay? What kind of data is up there? Or what's significant about it? Well, I'll tell you, it works with numeric data, it works with what's called categorical data. Neural networks work with any kind of data, which is very powerful. Many of the classical techniques, what would you suspect? The classical techniques, which are called statistical learning techniques, only work on what? Yeah, just pure numbers. Neural networks can deal with natively, quite easily, categorical data, and what we're finding now is more and more data is becoming categorical. That's kind of the stuff that counts a lot. So the goal of this problem of a neural network and their alternatives is when you have something like this, you want to make predictions. A classic example is predicting the stock market, where you would have not just a few of these, you could have dozens or hundreds of these predictor variables, and your thing to predict would be buy, hold, or sell, something like that. This is, you may have heard of the Wall Street quants. This is what they do. Okay, now, this next part is sort of conceptual of what goes on here, but it's really meant to identify somewhat of the issues. So this was on the far left is that last row of data that we were trying to predict. So the age of we're trying to predict the political inclination or party of this unknown, or this person. So their age is 38, their income is 51,000, their sex is male, and their religion is Presbyterian. The green arrows on the left-hand side indicate Well, can you infer what's going on there? What's the first step in a neural network? It's those green arrows. Yeah, I heard a couple answers. Data normalization or data conversion. Neural networks inherently work with pure numbers, but the first step is to convert them. In this case, 38, there was no processing other than to convert an integer to a continuous data. The income, 51, we scaled it down. We don't want some numbers being massively large compared with other numbers, because then their weight, that factor would outweigh other factors. Interestingly enough, this is a little bit tricky. Now, if I would have asked you to encode or translate sex, male or female, into a number, what's probably the most obvious way to do that? 0 and 1, right? However, this is one of those tricky issues. If you do that, that's like one of the, what was the word, the landmines in neural network thing. If you would do that, your chances of getting good results are very slim. It turns out that if you have binary input or predictor data, you should always encode it as, can you guess? Yeah, -1 or +1. And you go, well, why is that? Well, those are one of the issues that you'd have to figure out. See, these technical details. Then the last part is encoding categorical data that has more than 2 values uses a technique called 1 of n encoding, where I kind of botched this, but the first one would be how much Catholic they are, the second one is how much Presbyterian they are, and the third one is how much other they are, so to speak. So this person has no Catholicism, all Presbyterianism, and no otherism. Okay, but anyway, that's the encoding thing. That's one of the issues you have to figure out. Now, ultimately, for most of you in this room, you will not be creating a neural network from scratch. You will act as a consultant explaining your data to a consultant or a neural network expert, where your expertise is going to be understanding your data and being able to explain it to him. In other words, the key thing there was, in our data system, sex is encoded as either male or female. There's no other category, because that would make a difference. See, that's why you have to know this, I think. That's my point, and I'll talk about career implications later. Anyway, once you do the data transformation, it goes into that green box as kind of the neural network, and I'll show you another picture out there. And those things are nodes, and it simulates neurons and synapses, biological neurons and synapses, and I'm sure you all have a rough idea of that, but the nodes are like neurons, and there's connections that I don't show in that picture that combine, they're like synapses. Anyway, that information sort of like flows through, and I'll give you a concrete example in a minute. And then out spits, the important thing is the output is numeric. Okay? So the input is numeric, the output is numeric, but that numeric output can be translated into meaningful classification. Now, this is I actually did run this. This is the actual, I punched this through an actual neural network using that data from before. Can anybody guess what's going on with there with that 0.63 and that 0.37? Yes, somebody over here, those numbers, the output numbers can be interpreted as probabilities, numbers between 0 and 1 that indicate how likely that person is. So, does someone want to express a conclusion in English? This slide says that what? I'll start you. This slide says that, given the data in the previous slide, if we have a person with an unknown political party affiliation who is 38 years old with $51,000 income, who is a male and whose religious preference is Presbyterian, then what? Right. There is a 0.63 probability that they are a Democrat. Okay? Now, at this point, you could leave, you could leave and hopefully have some really valuable information. You understand really the most important part about neural networks is what kind of problems do they solve and kind of how they work, and to some extent, why this might be important to you. Because I tell you, every company in the Pacific Northwest where I work, Amazon, Microsoft, everybody is all over this machine learning of big data. It's really fast growing. Uh-oh, I hope you didn't catch me because I did make a mistake. Yes? Oh, so here his inference was, or the comment was, just looking at the data, he would have predicted Republican. Well, I was thinking about asking you to go through here and say, well, let's look at them one at a time. Just look at the age. Does anybody get a feel for it? I tried to make this realistic. I mean, it's fake data, but I tried to make it real. What's the relationship between age and politics, roughly? Right. Older tends to be more Republican, younger tends to be more Democrat. What about income? I'm sorry? Right. Higher income tends to be Republican, lower income tends to be Democrat. By the way, these are true statements based on the Statistical Abstract of the United States. It's where I go to get my data for stuff like this. Now, I have, sex, male and female. Males tend to be Republican, few. Anyway, and so on and so forth. The religion, that I did not get. I had no idea. That was just completely faked. But we're looking down. So age we have, age is kind of right in the middle. I made it deliberately tough to pick out. So age is kind of in the middle. Income, slightly high. Male, and forgetting the religion. So it's kind of, if you had to predict, it would be age, I don't know, income, slightly Republican, sex, slightly Republican. Okay, so you're taking into account the religious thing. Yeah. I will tell you, though, that, neural networks solve very difficult problems. So I'll say that I deliberately made this one quite ambiguous and difficult to predict. Okay, now, this is sort of a very technical information. Again, I don't expect you to remember this once you walk out, but I'm going to present it to you so that you can hopefully remember it when you look at it again. The building block of a neural network, remember how I had that green thing with a bunch of dots? Okay? Each one of those dots is called a perceptron. Perceptrons were the precursors. Now, to neural networks. Perceptrons were invented in the mid to late 1950s. And one of the horrible things about the vocabulary is completely inconsistent in this field. So sometimes neural networks, you'll be reading about neural networks, and all of a sudden they'll be talking about multi-layer perceptrons. And you're going, what? Wait a minute, I'm trying to read about neural networks. But a neural network, each one of these is a perceptron, so sometimes neural networks are called multi-layer perceptrons. Perceptrons, when they were first invented, it was just one like that. So they're very simple. So they only could solve simple problems. But by putting them together, a whole bunch of these perceptrons together, you get what's called a neural network. So there's kind of like a vocabulary thing. Now, here's what's going on. The 0.1, 0.2, and 0.3 are inputs. The W0, W1, and W2 are weights. And the B is a bias value. To compute the output, so there's some numeric inputs, and the question mark is, what is the output? Well, you just combine them. You multiply each input by its weight and add. Input times weight, plus input times weight, plus input times weight, and you get that intermediate 1.2. Then you add in the constant value, just think of it as constant, 2.0. Now, if that was all there was to it, you would just have algebra. The thing that makes neural networks work, the secret sauce, is this thing called the activation function. This is one of the 6 to 8 key things you have to know about neural networks. So I call it just activation. And the problem is, as someone who works with neural networks, you have to figure out what activation function to use. There are 4 possibilities. But here, we'll just say you do something with the 3.2 and you get out the 0.73. And so D, the output is 0.73. So really it's pretty simple. You just take some numeric inputs and do some fancy footwork, some shuffling, but the key thing is this activation function. That's what makes neural networks different. It seems like a small thing, but it isn't. Okay, so if you are going to act in some capacity dealing with neural networks, you have to, there's no getting around understanding what are the 4 choices of activation function. The bottom line here is this, that whether or not your neural network will accurately predict something depends on several things. And one of them is which activation function you use. Now, obviously, I think I got carried away here and I got a little bit too mathy. Sometimes, you know, when you're putting together a slide, you start wanting to impress other people rather than making it as simple as possible. So I'm not trying to, you know, with all the fancy equations and stuff there. The point is this, an activation function, those are the 4 ones. Those are the 4 possibilities. There are others, but they don't matter, okay? They all accept any possible value. That's x. I stop it at -10, but it goes off to -infinity, goes up to +infinity. You can feed an activation function any possible number, and it will spit out a number in a very contained range. Now, the contained range is either from 0 to 1 or from -1 to +1, okay? And that's called squashing, and it kind of makes sense. In other words, you take any possible number and constrain it or squash it down. Now, the logistic sigmoid squashes the output to between 0 and 1. The hyperbolic tangent between -1 and +1. The Heaviside step doesn't give you a range in between. It's either 0 or 1, not anything in between. And then the softmax is something between 0 and 1. So this is technical details. This is one of those things that you have to understand. And on my last slide where I list the references, I list the reference that explains that in detail with everything you need to know and no more. Now this slide is the classic, if you do an internet search for neural network and you pull up almost any of them, you're going to see something like this, first thing off. This is considered the standard kind of picture. I don't really like it that much, but it's just, this picture is a summary of what I've told you so far. So so there are 3, one of the hardest things about neural networks is the vocabulary in the field is completely inconsistent. This might be called, it could be called, is sometimes called a blank, where you have to tell me what blank is, a blank layer neural network, where blank is a number. What would blank be? 3. 1, 2, 3 layers. But in fact, it's usually called a 2-layer neural network because the first layer of input doesn't count. You're going, oh, great. Okay, so in other words, there's all kinds of, when you're reading up on this stuff, you have to be very careful about it. This would also be called a 2-layer or a multi-layer perceptron with 2 layers. So there's input numbers, and you can see, 1.0, 2.0, and 3.0. Then they go to the hidden layer, and one of the big deals here is like, why are there 4? One of the issues that you have to determine is, how do I know how many hidden layer neurons to use? The answer is, no one knows. That's the trial and error. This is one of the reasons why neural networks, you can't just like punch data into a neural network and presto, there's the magic prediction. It's an art as much as of a science, and one of those arts is determining the number of hidden neurons. Now the output is, that depends on the problem. Like the Democrat-Republican, you can see that in that kind of a case we would have 2 outputs. Down there in the lower right, that's the fancy Greek thing. One of the things, my message here is, don't be intimidated by the fancy Greek stuff you see when you read about neural networks. These things were all done by mathematicians in the 60s and 70s because computer scientists didn't jump onto it. Therefore, the whole field is heavily mathematician biased, which means that they love to throw Greek letters around. Not because they're showing off, because that's the language they're comfortable with. Can anybody guess what's going on down that Greek symbol, which looks like an O with a line straight through his Greek letter phi? I think it's pronounced that way, phi. And then the sigma means sum or add up. Can anybody interpret what's going on here? It's kind of, if you see, most people, would look at this and just immediately brain off, just forget it, it's Greek letters. But it's really kind of simple. This means add up. And what does it mean in algebra when you put two letters together? You remember this from algebra. Yeah, multiply. So you multiply x times w, and then add b. Does anybody remember from the previous slide? X is the input, and w is the weight. Multiply the input by the appropriate weight, then add the bias. Then you take that whole thing, and what would the phi mean then? That's the activation function. So it's just a concise way of saying what we described in words. You just multiply, add, and then apply some function. So, moral, don't be put off by the Greek. It's really pretty easy if you stop to look at it and figure it out. That's a very good question. The question was, notice here, the question was, are you going to use the same activation function or not? Now, what does this slide indicate that I should have pointed out? Yeah, there are two different activation functions. And in fact, that's quite correct. It is often the case that you want different activation functions. And that's one of the keys here is, like I mentioned before, how do you determine how many hidden nodes there are? Trial and error. How do you determine what activation functions to use? Trial and error. Although there are some guidelines. We've got about 12 minutes left when we get to the good part, when I explain to you how you can go beat Vegas. Okay, now, at this point, most of the people that I've talked to who are in the IT world, the developer world, they go, okay, wait a minute, okay, I kind of get it, I understand what problem, but this is just too complicated. There's just too much details. When you're learning about neural networks, you will reach the point where you think, man, every time I have figured one of these issues out, here comes another issue. It just seems like there's no end. Well, believe me, there is an end. There are roughly 8 issues that you have to figure out. And then it stops. And once you figure out those 8 issues, then you can start mastering it. In other words, you're still learning new stuff, but there's not like all of a sudden you're blindsided by this unexpected issue. So there is a discrete, roughly 8 issues. For instance, how many hidden nodes, which activation function, and so forth. And another one of them is, how do I encode or transform my data? Okay. So let me look at the bottom part here, neural networks pros and cons. The pro is, and this is sort of like a mathematical pro, it turns out that it's been theoretically proved that a neural network can model any set of data. In theory, it can predict, no matter how complex your data is, in theory, which is the key part, it can predict any function. Now, many of the alternatives can only predict data. For instance, maybe you took a stats class in college, and if you did, there was a topic called linear regression, which is a way to predict data. However, linear regression can only predict data that falls on a straight line in some ways. Okay? Neural network can predict data that follows any kind of crazy underlying model. Another pro, it can handle multinomial output. Okay? It turns out that this is sort of an interesting but important thing. Most machine learning techniques, surprisingly, this is really surprising, most machine learning techniques can only deal with problems where the output is binary. Meaning what? One or the other. You can only predict male or not male, bi or not bi. Neural networks can predict bi-cell hold, multinomial. It's one of the few techniques that can do that directly. So that's a big advantage. Now, the other techniques, if you get such a problem, you have to resort to trickery. So the con of neural network, quite complex. I would say, in terms of issues, it's the most complex machine learning technique. So that's the price you pay. It can solve anything, but it's the most complicated. Is that a surprise to you? No. I mean, that's the price you pay. The cons. Here's some of those issues. You've got to figure out how many hidden nodes. You've got to figure out what activation functions and the encoding. So those are 3 of the issues we talked about. Some more cons. The other con, this last con is really a continuation of the con right above it. I just couldn't fit it all into one line. A training method is another one of those 8 issues. The training free parameters, sort of a close cousin, same idea. And overfitting. Right here, those last 2 con lines are, depending on how you look at it, those are the issues that you have to understand. But once you understand those, then you've got it down. Here are the 6 main alternatives. I have never seen this put down. At Microsoft Research, every summer we have PhD students come in to do internships. And every time, their most pressing problem is that they have a problem that they understand, and they know one way to solve it, but they don't know what the alternatives are. Well, here it is, and I've never seen this anywhere else. If this PowerPoint presentation has any long-term value, it'll be right there. These are the 6 major alternatives to neural networks. Linear, and I'll just leave them up there, and you can look them up. But the point is that there are alternatives. There's dozens, but those are the 6 main ones, the ones that count. So we'll leave that as information for later. I don't want to go through. Each one of those could have a whole talk. Okay, now, one of the issues, and it was a con, here's another one of those 8 issues, where I'm just giving approximately 8, is how do you train the neural network? Training the neural network is the process of, if you remember, there's all those weights. Now, the inputs are part of your data, but those weights that you have to multiply, the problem is, where do those weights come from? Training the neural network means the process of finding the weight values, they're just numbers, that make the neural network work. So how do you find that? And that's the real challenge, other than encoding. And it turns out, again, there are 3 main approaches. Okay, you can probably answer me this now. How do you know which one of them is the best? Trial and error. If there was one best one, what would this slide read? Right, the way to train a neural network, okay? Back propagation is by far the most common, but I'm a researcher and I've done a lot of research. I think it's the weakest. There's a lot of controversy about that. It's very fast and is very mathematically elegant. So I think that mathematicians like it because it's very elegant. But I'm a practitioner. You know, I want to actually make predictions of my data. It rarely is the one that works best for me. The genetic algorithm. Have you heard about this, a genetic algorithm? It's an algorithm that simulates, so it's kind of weird, it simulates the behavior of DNA and chromosomes, okay? But it can be used to find the best set of numbers. And then particle swarm optimization is another technique that's fascinating, and it simulates flocking behavior. Like, have you ever seen those, usually it seems like it's in Africa, where there's some African tree and there's like a zillion birds flying, and they all move kind of at the same thing, and it's kind of eerie. Or schools of fish, same thing, they move and they keep together. Well, particle swarm optimization is this really strange thing. And I'll leave those, the 3, and here is a screenshot, and of course I don't expect you to go through it, but maybe later you can look, and it sort of gives you, if you go through it line by line, it gives you a very clear explanation of what that training process looks like. So I've got some raw data and blah, 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 and it explains it. I mean, it looks like a bunch of gibberish, but it was designed to be a tutorial, not just like spewing out log information. In fact, that's coming up in a slide never. The question was, how do you know when you're correct? How do you know when you found those best weights? The answer is, you don't, or you never will. And that's one of the issues. It's called, well, we'll get there in a second. But good question, good observation. So training, that's one of the issues. How do you train it? You've got to choose one of the 3 choices. Now, this is sort of really the same slide. I had the same slide, but I separated it out. Think about what I said. Training the neural network is finding the weights that best fit the data. Now, best fits the data means has the smallest error. So you would think that, okay, error, did you get it right or wrong, would be a simple thing. But it turns out another one of the 8 issues is defining what you mean by error is surprisingly tricky. And there are 3 ways to do it. How do you know which way to do it is best? Trial and error. This one's a little bit different. The top one, I put this up, percent accuracy, is commonly used by beginners, but again, based on my research, I think it's a big mistake for technical reasons. Sum of squared deviations, that's, again, if you're a mathematician. Okay, I mean, it's real simple, okay? How old are you? 32. I'm 62, okay? The difference in our ages is 30. 30 squared is 900. So that's sum of squared deviations kind of thing. It penalizes really large numbers. So it penalizes large errors. But that's a detail. But I mean, the real point of this thing is this is one of the 8 issues you have to understand. How do I define training error? Because there's different ways to do it. Cross-entropy error is kind of a special case that's kind of obscure. And that's why I put it on there. If you need to know more about it, read up on it, and I will point you to where all you find. I will give you the exact place to find out information on all these things. Okay, now your question was, how do you know when to stop? Here's another one of the big issues: is when you're training the neural network to find those values that make it work best. It turns out, imagine that you just randomly try values. Okay, for 1,000 years, okay? Eventually, you're going to get the set of numbers that fits your data perfectly. It'll fit perfectly, sooner or later. But the problem is, if you go back, remember the kind of problem it solves? You have some what's called training data, where you've got the known answer. And then all of a sudden, you've got to predict unknown data. Well, look at this roulette example. It goes, imagine that you're sitting there watching, and you could be your own neural network. Red, red, black, red, red, black, red, red, black, red, red. Yeah, anything. From a roulette, it's 50-50, except for the greens. But if you fed that to a neural network, what would and you trained it for long enough, that neural network would predict with 100%, I'm 100% certain that the result will be black. What it's done is it has overfit the data. It has worked too much and fit it too perfectly. Imagine, I'll just do a hand waving thing. Suppose we've got some dots, 3 dots, here, here, and here. Okay? And the thing that fits it best is a straight line. But you run it on the neural network for 1,000 years, and it generates a really crazy line that goes like this. But that line runs perfectly through those 3 points, okay? Because you overfit the data. You did too much work. So, I'd say avoiding model overfitting is the toughest challenge. It's one of the 8 issues, but how do you stop it? And so what it is doing too much work, and there are 5. 1, 2, 3, 4. Oh, there are 5. For me, this is, trial and error and very kind of difficult to get at. The one thing I'll just point out that I find very interesting is this jittering. It's something that you might not have expected. And that is with your true data, you add in deliberately false data. And you go, what? That seems to make no sense. Why would you put in deliberately false data? Well, if you put in deliberately false data, there is no way your model can become overfit, because it's going to come overfit on the false data, which means, do you kind of get the idea? It's kind of a difficult idea to grasp. Okay, I think we're winding down here, so I'm going to finish up. It's been 45 minutes. These next 2 slides go together. If you're going to deal with neural networks, you have 2 choices. Number 1, you can use an existing tool, which just means a software program. The most common one is called, it's from New Zealand. I pronounce it Weka, but they actually have a pronunciation guide. It's some sort of a New Zealand bird or something like that. They pronounce it like Weka, but I can't say it. But it's a tool, and I have a pointer to it in the back. But it looks like this. Now, if you look closely, look at the upper left-hand corner. What do you see right away? They're not even calling it a neural network. They're calling it a multi-layer perceptron. So that's, we know it's a neural network. Then all of those parameters, dash L, dash M, dash N, dash V, what do you suppose those are? Those are options to it that describe to the tool what kind of activation function to use, how many hidden nodes to use, and so on and so forth. Okay? And then all of that jumble, sigmoid node. What does that suggest to you? Well, you didn't notice it probably, but one of the activation functions is this called the sigmoid function. So apparently, this is a sigmoid activation usage and so on. The other alternative is to code up a custom solution. And this is a C# program. And again, it's mostly just to give you the point, but you can see up at the top, number of input, number of hidden, number of output, and those have to be specified. Okay, so we're winding up here. So let's see what the summary is. Well, the second bullet point is that, the point of neural networks and why they're becoming increasingly looked at is that because enterprises now have a lot more data and have access to the data and can get at it, neural networks, see, there's a heavy investment, right, to use neural networks, but now that investment might pay off, okay? So people are taking a much closer look at neural networks on big data. Well, by the way, big data. What is big data? No one knows. It just means lots of data. Now, the top one is, again, I mentioned this before, it's not likely that you're going to go in and code up your own custom neural network thing. It's really pretty complicated. You could do it, but it would take you a long time. A much more likely scenario is your expertise is understanding the raw data. In other words, imagine where you're working, and you call in a vendor or call in somebody, a consultant that uses the tool. The hardest part, if that person doesn't understand the data, they have no chance of making a neural network on it. So your value is as a consultant thing. One of the main themes in IT is IT people are moving closer and closer to strategic business value as opposed to, like, I don't know how to put it, like operations support. In other words, you're not just there to keep the email up and running. You're there to help generate valuable information for the sales department and provide, revenue opportunities for the enterprise instead of, because let's face it, if you had a company and there was some department that was purely support and you could ditch that department and get the same functionality at half the cost by outsourcing it, what would you do? Well, you do it, okay? But for an IT department, as IT departments, and you in particular, as a career path, this is something for you to consider, and that's what I bring. So, consultant, you got to understand. See, that's when the consultant is going to talk about, well, we're going to try this activation function or that activation function, and you say, well, you'll know what he's talking about. You may not know the details, but you go, okay, yeah, I understand. That's an issue. And here I put down, this is sort of a speculation. One thing is that this use of neural networks is still very niche, but it's going to grow. It's something for you to consider, and that is to learn more and more about it. Because I can tell you right now, we did a study at Microsoft about 3 years ago where we wanted to find out, I was tasked with finding out the most authoritative neural network implementations code available on the net. You know what the most authoritative one was? Some guy, a teenager from Romania, on his personal blog. That was the most authoritative neural network implementation available. Well, that's changed now, but it's still a very niche area and not many people know about it. It's something for you to consider learning more about it. Here are the 4 resources. The theory, all the questions, the vocabulary, and I don't think you can write this down, but I don't think I'm going to give you enough time. This thing is posted in several places, but this is the most stable location, okay? The SAS Corporation, they're a statistics company, so they've posted this information that appeared somewhere else, and it's usually there. Weka is that tool, and that's where you can find out about tools. Custom C#, MSDN Magazine is the source, the authority for that. And then this presentation, if you write down one, write down that, because it's not up there yet. But when I get back to Redmond, I will post this presentation, minus anything that I can't, which shouldn't be anything, onto that blog site. And that's the end. I knew this was going to happen, so. Justin, we botched it. What happened to my sound? Maybe not. Oh, shoot, I had this all worked out with Justin the other day. I had a recording of clapping, really loud, and bravos and cheers and woohoos. Oh, man, I botched it, though. Anyway, thank you very much. So if you want to stick around and ask some questions, we'll do question and answer for about 5 minutes only, because then I'd rather make myself available somewhere else. But then after that, I'll do 5 minutes because we got done early, and I'll explain briefly how you can beat Las Vegas while you're here, win lots of money, and possibly get thrown in jail. And also, I'd like to encourage you to fill out the course evaluation on whether or not you like this type of thing. You know what I mean? I think you understand that this was not like, okay, yeah, how to use Systems Center or something. You know, it's a forward-looking kind of off. We call it an out-of-band topic. And I enjoy doing it, so if you like it, say good things. But if you don't like it, say that too. You know, just say, oh, this was, you know, not a good use of my time. We'd rather have something more solid about it. Okay, any questions? And here's where half the room is going, please, nobody ask a question. Please, nobody ask a question. I want to hear about Vegas. Yes? I'll rephrase the question as when did Microsoft start looking at neural networks and sort of what's the strategy and stuff like that? It's very surprising. Microsoft Research has been, of course, looking at neural networks since the beginning of Microsoft Research. However, there's a certain initiatives going on right now, and there's several of them, where we feel it's important at Microsoft to place, and I'll call it machine learning, place machine learning knowledge in the hands of the IT community. So there's several ways to do that. And one of them is through MSDN Magazine, where I'm a senior contributing editor. And that's where I'm mostly a developer, and I write that. Another way is through talks like this, to expose you to this information. So it's a relatively recent thing, and there's multiple prongs aimed at different audiences designed to get it. But it's been around forever, but it's been sort of evolving. So that's not a really good, solid answer. In other words, but that's the best I have. The question was, have neural networks made it into any of the products yet? The answer is, I can't really answer that, because that would be, some of that is considered sort of proprietary product information. But I can tell you, obviously, all of the major players are using looking at neural networks as a possibility to give them competitive advantages, both for their products, but also for their back-end operations kind of thing, sales information and things like that. Okay, now, Vegas. Oh, wait, question? So the question was, or the observation, which is correct, is that they're not the same, overfitting and small sample size. If you have a small sample size, your chances of getting a good neural network are nil. In other words, neural networks in general, compared to other techniques, require lots of data. As a rule of thumb, I'll just give a rough rule of thumb. If you don't have 1,000 observations, neural networks are probably not going to give you good answers, as a rough rule.